Katja Hofmann. She is a partner research manager in Microsoft Research. Her research combines modern machine learning techniques with human AI interaction and social science. Today, she's going to present a generative word model for interaction and imitation. So without further delay, let us welcome Katja.
Fantastic. Thank you so much for the kind invitation. It's a pleasure to be here, and I've been very pleased to hear the many mentions of interdisciplinary research in the opening and the chair's welcome this morning. My name is Katja Hofmann. I'm a partner research manager at Microsoft Research in Cambridge, where I co-lead a research area called People-Centric AI. We have established this research area with the goal of creating a fundamentally multidisciplinary research area that spans from machine learning to HCI and the social science. And the reason for that is that we believe that as AI, machine learning techniques rapidly evolve and produce better and better models and artifacts, there are some key challenges in making sure that this is not seen as a runaway train, but that rather we design the models, the tooling, the experiences around this technology in such a way that they truly empower people. Now, my work doesn't specifically focus on science or AI for science, and at the same time, I think there is a lot of overlap. Ultimately, there are key questions about how people will be the ones in control, empowered by the technology that we develop. And a science, for example, is a fundamentally creative human endeavor. So how do we make sure that the people in charge of this can use the technology we develop as effectively as possible? Across the research area, we have a number of projects. I will be focusing on two of those that I've worked on particularly closely. But if you would like to discuss other related topics, such as how to design experiences that support critical thinking, which was done in recent work around tools for thought, two questions around provenance, for example, how can we ensure that people can understand where information comes from or where, for example, images or other generated outputs have originated, whether they're real or not. Those are also topics covered within the research area, and I'd happy to chat with you and refer you to the right collaborator in my group. Then for today, the key areas that I want to focus on are two topics that are closely related. When you come to this from a reinforcement learning perspective, you will roughly be able to map this to the standard picture where you have an environment on the one side, you have an agent on the other side, and then they're connected with arrows where one sends actions to one and the environment sends state observations to the other. A lot of this work comes from reinforcement learning, but I will not be talking about reinforcement learning per se. Rather, I will be looking at how we can learn models of complex environments, in this case of modern video games from human gameplay data. And then similarly, I won't be looking at behavior in the context of a reinforcement learning agent, but we'll be looking at how we can derive techniques that are as data efficient as possible in imitating complex behavior within 3D environments. Both of those come from motivations around how to empower people. The first one is around how to empower creatives in kind of independent uses of the kinds of world models that we're able to learn. And the second one looks at how complex tasks can be automated, again, for people who want to offload repetitive tasks to agents. There are many other connections, and in the context of this interdisciplinary discourse today, I'd also love to hear your insights, your ideas on how these might be applied in different contexts, and especially in scientific endeavors that you might be looking at. So without further ado, we'll jump into world and human action models, playable worlds that can be learned from human gameplay video. To give you a sense of what's possible today. So last April, we released a demo where we had learned to simulate a video game, in this case, a level of the game Quake 2, purely from the visuals that a player might have seen on the screen and the actions that a player took in response to this. This model was learned from less than 100 hours of data, which has been collected over the course of a week or two. And I want to play a video just so that you get a sense of the quality of what's possible to learn. So what you see here might look similar to the video game that we're simulating, but this is entirely generated on the fly in real time in response to the player actions. So you can see here at the bottom the controller actions that the player is issuing, and you can see the visuals that are generated in real time. Real time for us here is 10 to 15 hertz, but it's fast enough to get a smooth play experience. This is actually deployed as a technical demo on copilotmicrosoft.com/gaming. So if you want to try this out for yourself, in the online version, there's slightly more latency than what you see here in our internal demo, but it's definitely a quite playable experience. So I hope that gives you a sense of what we can learn from human gameplay data. So from non-game specific sample of image action pairs in such a model. Before I go into the details, I want to take a small step back and give you a sense of the kinds of things that creatives ask for when we show them these kinds of experiences. So we did a very small kind of focus group last summer where we showed 3 creatives ranging from a game creative to a marketing creative and an industrial designer. We showed them a prototype with the kind of interactive experience that I just demonstrated to you. And we asked them about kind of their thoughts on where they would use this kind of technology. And so here's the result of the thematic analysis within that. And I think they're quite interesting because they can help us prioritize some of the key research directions within that. The vast majority of what we have worked on so far in terms of technical capability is related to this first cluster on rapid creative prototyping. So in the words of one of our participants, they were excited about the possibility. I want to come in the morning with new rule ideas, submit them to the AI, and directly play. So they were really interested in this notion of, I have an idea, I can kind of create an interactive environment where I can try these out, maybe in a prototype form, maybe not in high visual fidelity, but it's enough to directly go and play in real time. And that would be a major change for them from the current setup, where they come up with an idea, it takes weeks to set something up to be able to play and test this out. Key capabilities that might be required to push this further are real-time inference, very fast fine-tuning on small data sets, so very data-efficient learning, as well as controllable generation without machine learning expertise. And so in the first part of the talk, I will primarily focus on how we make progress towards those 3 characteristics. Further out, our participants saw key opportunities around creating infinite narrative worlds and democratized experiences. Talking about narrative worlds, the participant who is a game director can be quoted as, whoever you grab becomes your partner in the story. There's unlimited death wherever the game goes. So this would go beyond games where, for example, challenges have to be scripted or created in some way, to something where you open a door, any door you open leads you to a new aspect of the story. Key technical requirements for enabling this would include persistent memory over extended sessions, long horizon narrative coherence, or multi-agent coordination with distinct goals. And in many of these areas, we're still at a very, very early stage in the research. And so I want to emphasize there's a lot of really exciting opportunities for improving over what we have today. Finally, the participants saw opportunities around what we termed here democratized experiences. So these are experiences that go beyond gaming, that might mix virtual and real aspects of environments. For example, one of the participants expressed it as, what's a masterclass when you can actually talk to those people and walk in a garden with them? So think about the kinds of technologies that would enable virtual concert experiences where you can directly interact, for example, through multimodal interactions, where there might be audience scale, real-time generation of the experience. And so some of the challenges in this space and how we're making progress in that are mapped out over here. So as mentioned, I hope this gives you some sense of where we might be heading with this. For the majority of the talk today, we'll be focusing on technical capabilities that could unlock rapid creative prototyping. And at the same time, in addition to those creative use cases, I do see key opportunities around science and discovery as well, and would love to hear your thoughts about this in the Q&A or after the talk. Thinking about the requirements for rapid prototyping, I want to give you a quick overview of roughly how the work within my team has evolved over the last year or so. In February 2025, we published WAM, World and Human Action Models, towards gameplay ideation, which was published in Nature. And the key breakthrough there was to demonstrate that from an appropriately large and high quality data set of visuals and actions collected in a game environment, we were able to train a consistent model of the original game environment. The model was purely autoregressive, which resulted in this relatively slow rollout over here. This one is actually a video, and you can see in real time how kind of fast it was able to generate game clips in that particular example. We then invested in the real-time capabilities that I mentioned as kind of key requirements before. And in April, we published the technical demo and a blog post about WAM. We now renamed this to WAM-RT, but the key advance there was to show that real-time inference on these kinds of models is possible. Now with work in progress, we're at XGA resolution and real-time. And so we think that we're approaching a setting where these can be at high enough quality and high enough speed to enable kind of any application that requires these kinds of high fidelity, immersive kind of models of game environments. The vast majority of this part today, I want to talk about WAM because it gives a good foundation of how we approach these models, but I'll also give you a glimpse of how we went to real time and a first proof of concept of controllable environments. So starting from WAM, World and Human Action Models, towards gameplay ideation. We have seen I've given you a sense of what's possible with these models, and so I want to now dig a little bit deeper and show you what's under the hood. What's under the hood in WAM itself is maybe surprisingly simple model architecture. The key kind of insight there was that we can directly leverage all the technology that has been developed for large language models in order to model other modalities, such as game environments. Key here is that we need to encode the images that we receive from the environment and that we want to generate. We need to translate them, in this case, into a token-based representation, which we do using an encoder-decoder architecture, which is trained to give us a latent representation that preserves as much information about the image as possible. In the latent state, ZT, we then have a series of numbers, a token-based latent representation, in this case here, of length 540. And we similarly, well, not as complicated, but we also encode the actions that we see from the player. From this, we can now construct a sequence of tokens where we interleave the representation of the image, the action, the next image, the next action. And now we can construct a predictive task where the task of the model is to predict the next token in the sequence, exactly identical to what an LLM does. And we initially, at least, also used a causal transformer to simply do next token prediction, illustrated here. And now from this very straightforward, very simple approach, when scaled up appropriately, we found that the model is able to learn the complex physics that we have seen captured in the models that I showed you before. I want to take a small detour here to emphasize that a model set up in this way as a world and human action model, so directly predicting next actions and next images, can be used in a variety of ways, and this was one of the key motivations why we set up the model like this in the first place. You can use a trained model in a behavioral cloning setting where we provide as inputs the images that come from the game engine, and we let the model generate the actions that a player might have taken in response to those to those image observations. We can use it in a pure world modeling setting, meaning that we might condition the model initially with an initial image, an initial state of the environment. We provide the actions of the player, and we ask it to generate the missing images, which means that we're essentially creating a simulated game engine that a player can now interact with. And we can use this for full gameplay generation. So we can start from a blank slate, or we can start from an initial image, and we can ask the model to generate images and control actions to fully predict what continuations of that initial image could look like. To say a little bit more about the data set, so the initial work on WAM was done on a large data set that we unlocked in collaboration with Microsoft Game Studio Ninja Theory on their 2020 Xbox game Bleeding Edge. This is a third-person combat game, 4 versus 4, and if I run the video, you get a sense of the complexity here. The image here is downsampled to exactly the resolution that we used in the majority of our research. As mentioned, we are now able to produce full resolution or XGA resolution gameplay. So this is from an earlier version where we were not yet able to do that. And in the initial work, we relied on a large data set. So in total, this is about 36 years of human gameplay across 7 maps and 2 game modes. And we primarily focus on a filtered data set that has 1 year of human gameplay on 1 map and 1 game mode. And something that's very interesting to see as we train this model and evaluate over time, we can see how more and more sophisticated understanding of the game environment and its physics emerge over time. After about 10,000 training updates, we can see, first to show you ground truth. So this is what comes directly from the game engine. We see this character move up the stairs. This is a character that has a special flying mechanic, which it uses here to cross this open space. After about 10,000 training updates, we see signs of life, but the quality deteriorates over time. So we see that consistency is not yet sufficient. That gets resolved after 100,000 training updates, where consistency works well, but not all special abilities are captured, such as the flying mechanic, where here the character just dropped to the ground. Finally, as we continue training, more and more accurate understanding of the game dynamics are built up. For example, here the flying mechanic has emerged after about 1 million training steps. We then looked at how to evaluate the model, and so one of the key contributions of the paper there was to propose 3 dimensions of evaluation that were well aligned with needs of game creatives in this particular case. First, we needed to ensure that consistency is high and that hopefully it scales well. So we here show that consistency of the model improves as we train larger models on more compute. We measure consistency in terms of video distance, which is a distributional measure comparing the generated images to, or generated videos to what we actually see in the ground truth data. Lower is better, and we see that as we increase compute, so flops, and train on larger models, we get improvements in FVD. This is the interpreting distances in FVD is not necessarily straightforward, but we typically see that below an FVD of about 100 on this data set, we get a quality that is good enough to play within this environment from the perspective of a human player. We also looked at evaluating diversity. It's not we don't have a metric that I'm very happy with, so I'd love to hear people's thoughts on how this could be evaluated more systematically. Intuitively, if we have a learned environment model like this, we want to make sure that it's able to capture all the kind of meaningful ways in which people might move forward from a specific starting point. So it should be able to appropriately model interactions and the environment, whether we take the left, center, or right path. I can give you a sense qualitatively that the model is able to capture all the different diverse paths here. And this was evaluated in the full generation mode. So in this case here, both actions and visuals are generated by the model. To approach a metric of diversity here. We proposed the Wasserstein distance to the human actions, or to the distribution over human actions. And we can see that over time with training, the model approaches the human-to-human baseline. But as mentioned, I think there are a lot of open questions around how to appropriately evaluate diversity of a model like this. We can also show that the model can generate reasonable behavior, and while this has not been trained to achieve any specific behavior, if we start a character in a specific situation that is game relevant, such as close to seats or within a combat situation, we can see that the characters generate the appropriate behavior for that situation. Finally, again in the context of artistic uses and controllable behavior, we evaluated a notion that we call persistency. And to give you an example here, persistency means that a user of this model can make modifications to this. For example, here I can just copy and paste an image of a game-relevant item, such as a power cell, into the scene. And then if I start generation from this, we can see that the modification is persisted and then the interactions with this element are appropriately modeled. Similarly, I can copy and paste a character into the scene and get a combat situation. We can quantify this, and we did this with a human study, where we, for example, were able to show that persistency improves with a notion of in-context learning. If we condition on only one frame with a modification, we get 60% usable dreams. The kind of power cell persisted 14% of the time, and player characters 55% of the time, but that dramatically increases when we condition on 5 initial frames. Yeah?
Sorry, I'm just trying to understand. So you're saying you can add something to a specific frame and it will then persist in memory even when it vanishes from the screen. So you get sort of total object permanence. Is that what you're arguing?
I'm not making a claim about memory per se. So the kind of in the context of the model, you have a sequence of images, right? And it always generates then the next action, the next image. If I manipulate that context and I just copy and paste a different visual into that, now that changes the context of the model and it produces a continuation that is consistent with that modification. Does that make sense? So yeah, if you take the context as the memory of the model, then it has now changed its memory and you're getting the appropriate.
I suppose what I'm trying to understand, does your model contain significant memory of previous frames as part of this internal representation?
Mm-hmm.
And then how does that make sense? If I start just randomly adding things into the scene, that seems like it would break all of the training structure unless you've trained to do that.
Mm-hmm.
I'm just trying to understand what is being done.
Right. So the model has relatively short-term memory. So for these demonstrations here, we typically have on the order of 10 frames. We sample at 10 hertz, so that is 1 second of memory, which means if you stare at a wall for 10 seconds and turn back, there might be opponents, there might not be. So that is the extent of memory that the model has available to it. Now, I cannot copy and paste random visuals into these frames, but to the degree that a visual representation has been covered in the training data, like these power cells or the non-player characters that are part of the game, the model has learned enough structure to capture that this representation of a power cell will lead to downstream effects, such as the notion that now a player can attack it and can blow it up, and that there's the appropriate explosion effect, right? So what I'm saying is that the structure of, in a way, the notion of an object with a specific behavior is somehow implicitly captured in what the model has learned. Does it make sense?
But this, I suppose, is related to the fact that your model has very limited object permanence as a structure.
Right, and by object permanence, you mean over a longer period of time, such as longer than a second?
I mean a 3-year-old, when you cover their eyes, they forget things. Or 1-year-old.
Right. it's a goldfish. Yeah, exactly. So, right, and then if you want to increase memory, I mean, these are tiny models compared to large language models, right? We're training the smallest possible models we can get away with to prove a certain point. Now we have language models with a million-long context window. You could you could naively increase memory in that way and get to something that covers a much longer period of time, like a minute, for example. But I think there's also a lot more interesting things we can do in terms of how we build up the context of such a model to enable longer things, and I think that's the more interesting research direction. Yeah. In terms of object, I guess the surprising part here for me is that it's not beforehand obvious that the notion of what is a specific object and how can characters interact with that object. It wasn't clear ahead of time to me that that would emerge purely from predicting the next token. So to me, that is the surprising part. Great question. Thanks. So this was the kind of main part of world and human action models, and now I want to give you a kind of slightly faster paced sense of how we continued to, in more detail, understand the kinds of models that we have here and what they're able to do, and then also to unlock more of those creative capabilities than we were able to do here. So first, I want to give you a quick glimpse of work that we published at ICML last summer, which focuses on scaling laws for pre-training agents and world models. Like we mentioned before, the kind of underlying machinery here is a large language model, and so there was a question of, as we understand scaling better and better for language, would similar scaling laws emerge for these types of models when we look at the world modeling and behavioral cloning? Now, the kind of good news is that scaling laws, similar to those found in LLMs, also emerge in world modeling and in behavior prediction. What you see here are the scaling laws that emerge for two different world modeling tasks where we changed the size of the latent representation, and kind of interesting findings emerge when you look at the size and other aspects of that tokenization, which is something that is distinct in modeling images versus purely language. You can also see here BC tokens. So these are the kinds of scaling laws that emerge for behavior. And one kind of, if you glimpse at this, hopefully you can see that the structure here is a lot less clear for behavioral cloning, so for the action prediction part. So we see some key differences in how scaling works between purely predicting the next world state or next world observation versus predicting next actions. If we look purely at the world modeling side, we get nice scaling laws. They can even match the coefficients that we get in language modeling. And we see that extrapolation works. So we had this X here mark the spot of the loss we would get for a larger model that we hadn't trained before. And we can see that the actual loss of the model quite closely matched that prediction, which is good news because in a setting like this, we're often in a situation where we may have a specific compute budget, and now we need to parameterize the model appropriately for that compute budget to ensure that we've trained this to a kind of optimal loss with the compute budget that we have available. In the paper, we also dig deeper into the kinds of factors that impact the coefficient of the scaling loss. And for example, we find that there is some key influence by the compression rate of the tokenizer. So in this quick plot here, we see that higher compression skews the model towards more model parameters, whereas low compression skews towards more data. Meaning broadly that if you have a larger compute budget, with a lower compression embedding, you will have a model that is more data hungry. Now, the key interesting difference is when we look at behavior prediction. First version is that if we model behavior with the approach that I showed you initially, so we purely tokenize the actions like the images and we use next token prediction, then scaling laws are actually less clear cut And the models tend to be very data hungry, which is bad news in a setting where action data might potentially be harder to get at scale. The good news here is that we can move to model architectures that remedy this, and in the paper we propose one particular architecture that resides in more prototypical scaling loss. Again, I think there are some really interesting questions that arise here, especially around how we can learn behavior in a data-efficient way, where data efficiency is usually much more important for behavior than compute efficiency. So there's some interesting questions raised here by that. And the final piece of work in this context that I want to touch on is our work towards real-time multimodal world models for interactive experiences, looking both at how we can modify architectures to get to real-time experiences, and then also how to start making these controllable. So I showed you this architecture for WAM, where we purely use token-by-token prediction, which gives us high consistency, but unfortunately low speed. The key change that we introduced for WAM-RT, or WAM real-time, is that instead of predicting tokens one at a time, we now use a bidirectional transformer where a number of tokens are predicted in parallel. We are compartmentalizing that into two components. One, shown in pink, is a compressed context, so a compressed representation of the images and actions that are in memory of the model, plus a low-quality proposal for the next image that we're generating. So basically, there's a trade-off here. If we do token-by-token prediction, we can get a very accurate prediction of the tokens that make up the next image. If we generate them in parallel, we are very fast, but we get a lower quality prediction. And then on top of that lower quality prediction, we apply a mechanism that is very similar to a diffusion model, and in fact could be seen as a version of discrete diffusion, where now we have a small, lightweight refinement transformer that iterates over a number of steps in order to simultaneously predict, update the token until we get to a higher quality image. With that now, we can tune the number of iterations we do on the refinement transformer, and that gives us a trade-off between speed and image quality. I already showed you a demo of the real-time model for Quake in the beginning, and here we have a similar demo for the game Bleeding Edge, again showing that we can now achieve interactive play in real time. Finally, on this line of work, I want to give you a sense of how we're moving towards controllability. This is a task that we called Body Swap, where we wanted to create a proof of concept of introducing a new mechanic, a new type of controllability that did not exist in the original game. In that proof of concept, we created a aligned data set where we essentially edited the training data to cut from one character in the environment to another character in the environment. We, in this way, collected about 55,000 training examples, which now consist of 20 frame sequences, 10 of character A and 10 of character B, together with a natural language label of the type of character that was being switched to. And then we can modify this model by incorporating an additional direction. So, for example, playing as browser, so one of the characters in the game, or we can also use any other kind of language that was introduced in this data set. Play as a female character, play as a male character, etc. And then we get a model that is controllable in the way in which it was trained. If you look over here, we can, for example, set to a character play as Gizmo, set the prompt play as Azrael, and we get the change to the character. And as expected, with the character change, all the special abilities, the behavior of the new character is also incorporated. So those are appropriately captured. And from this proof of concept, we can show that we can introduce a new type of mechanic, a new modification into these kinds of models. With that, I want to close the first part of the talk here, focusing on world models. And next, I will talk about behavior with predictive inverse dynamics models. But before I go there, I want to briefly pause and just see if there's any questions on the world modeling part of the talk.
So to what extent do you trust the physics that is learning? I mean, do you trust the same mechanism to generate data for, let's say, trading self-driving cars?
Fantastic question. In a way, we have it easy here because for creatives and artistic environments, we may not have to trust them fully, which makes this a great experimentation platform. I think there is a lot of potential for self-driving cars and other embodied environments, but indeed that notion of what would it take to, in a way, certify a simulator, I think is a very interesting one. I'm not aware of any answers of that apart from statistical, right? We can have a held-out data set that we can evaluate our model on. In this case here, I can pick up a controller, I can push the boundaries, and I actually have after playing for a couple of hours with these simulators, I have a pretty good sense of what are the shortcomings, where does it go out of distribution. But it's quite there's the qualitative component of this, and there's the purely how does the loss behave on a held-out data set component. And I'd love to kind of get an understanding of what verifiability might look like. So I'm curious if people have any ideas on how that could be moved in that direction.
I was wondering if you could comment on the trade-offs with the behavioral cloning part of this. So I can see if you want the model to take realistic actions, then that's necessary. But at the same time, if you wanted to build a different model that's about exploration, it also might hamper use. But I can also see if you don't do behavioral cloning, then learning everything is really hard. So I was hoping if you comment on like how you deal with that trade-off.
Right. Great point. There's a lot of trade-offs here, and like I mentioned, the main motivation here for us to include it was that it gives us a wider range of uses that creatives might explore. We found that because of the way the losses broke out, in the vast majority of the models that we've trained, the world modeling loss dominates the behavior cloning loss. We have a small amount of anecdotal evidence that predicting both simultaneously does improve the world modeling component, but we don't have a very good, not even a very systematic evaluation of the behavioral cloning component. Now, in the second part of the talk, I will touch on behavioral cloning and how that can be improved. So there's some connections there, but I think we're still at a very early stage in understanding that connection. So, there's a question here.
In one of the pictures, when you show the scaling laws of different models, there is also a line called imitation frontier. Can you comment a little bit about what is this imitation frontier mean?
Yeah. Okay, so the question is about the efficient frontier in scaling laws. And so, as a kind of high-level intuition, when we talk about these scaling laws, we want to understand how we can optimally trade off compute and data into the lowest possible loss of a model. Broadly, when we optimally tune hyperparameters for a model, then we find that the model we find a kind of linear relationship with a specific slope that happens at the point where the model gives us the lowest possible loss for that particular compute data kind of trade-off. And that is what we call that efficient frontier. And we see that emerge kind of empirically, and that was kind of where some of those early insights on scaling laws for language models originated. There has then been follow-up work to kind of formalize that and to understand to what degree what we can say about that efficient frontier. For my team, it's primarily a useful tool to estimate how we need to parameterize a model for a given compute budget. But I think there's some key open questions on why these kinds of scaling laws emerge, right? Why would there be certain coefficients? Why would they be relatively consistent over different models trained on different data sets, for example? And for example, even here, we can get similar coefficients to emerge for modeling game environments as we get for language. So why would that be the case? And I think there's some really interesting questions there on even does that happen for transformer architectures? Is there something general about computation and how data is transformed into model insights? So yeah, very interesting. Okay. Any other questions before I move on? Right. So then in the remainder of my time, I also wanted to touch on the behavior side of things. In particular, there's a preprint that we put out recently in January, where we look at when predictive inverse dynamics modeling outperforms behavioral cloning. The motivation for this is the kind of task of learning in as data efficient way as possible to imitate tasks in a complex environment. And again, I'll motivate this with an example in a game environment. This happens to also be the game Bleeding Edge that we saw earlier. And in this demo here, we see a human player demonstrating a complex navigation task through this 3D environment. In the playback screen here, we see what happens when we naively imitate the human behavior, for example, by purely replaying the actions that the player issued while they were navigating this particular task. And we can see that even on an environment that is relatively deterministic, even there, the effects of latency can cause such a deviation that we cannot purely replay the demonstrator's action and expect to get the same behavior, right? And so, long story short, if we have unknown stochastics within a complex environment, we typically need to learn how to compensate for those stochastic effects, which then gives us the kind of challenge of how we can learn to imitate complex tasks with as little data as possible. Now, traditionally, well, there's been decades and decades of work on imitation learning, and so we can usually formally describe this as a sequential decision-making problem where we have a set of states, a set of actions, and a small number of demonstrations that give us a sequence of state-action pairs that were generated by the expert demonstrator. Now, our task is typically to learn a policy, so we want to have a policy that gives us an action given either the last state or the history of state observations, such that the generated sequences are under the same distribution as the expert behavior. Now, a standard approach in this setting is behavioral cloning, and as discussed earlier, even our world and human action models can be seen as an instantiation of behavioral cloning, where as input we get our sequence of states. We observe at training time a label, the expert action that was taken in that particular state. And our job is to learn a policy that minimizes the log loss with the expert demonstrations. So we can see that behavioral cloning does maximum likelihood estimation of the state action sequence. A key question that the team ran into here is whether behavioral cloning is implicitly modeling the desired future states. And pursuing this question led the team to insights on potential improvement over behavioral cloning, which is called predictive inverse dynamics modeling. You can kind of look at this as two key innovations. The first one is that we explicitly break down behavioral cloning into two subproblems. First, we try to predict the desired future state. And the second one is that given that desired future state, we do inverse dynamics modeling, given we try and find the action that maximizes the probability of going from state T to state T plus K. In terms of a small architecture diagram, we can look at this as something where we implement this with a state encoder, which gives us a lower dimensional representation of the initial state observation, which is useful if our state observations are images. We can use an encoder to also then use the same feature representation for both the state predictor and the inverse dynamics model. And then we have, instead of directly predicting the action, we now have two components. One is the state predictor, and one is the inverse dynamics model that tries to give us the action given the predicted state. This type of setup has also been recently, especially recently, proposed by other groups, and there were similar promising results. Initially, this work was very empirically. We found that behavioral cloning tended to be more data hungry and less robust than this type of approach, and that kind of led us to digging deeper into why this is the case. Another interesting point was that indeed other groups had found similar insights. So for example, looking at recent works, they found that, just bring all that up here, over approaches that were essentially doing behavioral cloning versus inverse dynamics modeling, we found that broadly those doing predictive inverse dynamics modeling, performance was better with the same amount of data. So now the question is, why does predictive inverse dynamic IDM outperform behavioral cloning, and under what conditions can it be expected to do that? To build a little bit of intuition here, broadly with this decomposition, we now get a bias variance trade-off where explicitly modeling the expert's intent can reduce uncertainty. So we get a reduction in variance. If indeed the prediction of the state predictor is accurate enough, so if we have low bias. And we can indeed capture that in theory. So we can show that the behavioral cloning policy decomposes into these two components of predicting the state and predicting the action using inverse dynamics modeling, which gives us the point estimators for behavioral cloning and inverse dynamics modeling with an expected prediction error that we can see decomposes like this. And the key takeaway here is that predictive inverse dynamics modeling is more effective than purely behavioral cloning whenever future conditioning helps to reduce uncertainty about the actions. The key assumption here is that, at least in the theory, is that we have optimal estimators for the state predictor. In the initial implementations where we validated that, we used a expert demonstration as the state predictor. So because we have a demonstration of the task, we can go along and look at the next state in the observed demonstration as the state predictor. And so that gives us a clean next state estimate, but a wide range of other components could be replaced for this. So for example, recent video models could be used to model the states that are likely under the human expert demonstration. So to summarize briefly key insights here, behavioral cloning can require many more samples than PIDM. The sample efficiency gains are a function of the state prediction error. And if in that state prediction error variance dominates, then the sample efficiency gains are greater than 1. And just to very quickly give you a sense of why this is so interesting, the architecture can actually be very flexible. So the state predictor and IDM can follow different model architectures. They can be trained on different data sources. The encoder is not necessary, but it does empirically show benefits because we can learn a common representation for state and action prediction, and we have found that this makes it much more data efficient. And we have also typically used a multi-step inverse dynamics model, which can further reduce exogenous noise. Interestingly, each component can be trained with additional losses and leverage different joint embeddings, which makes this a very flexible starting point for a lot of interesting empirical work. To close this, I just want to give you a sense of the kind of behavior that can be learned with this. Again, this is the same, an extended version of the task we saw initially, learned from 30 demonstrations. And this has blanked out which one is the human and which one is the learned behavior. So we can use this as an exercise to the audience here. Who thinks the one on your left is human? See, who thinks the one on your right is human? Okay, we get a lot more human here. Now I need to convince myself. This one is actually human from what I remember. solution here. There we go. So I want to close here so that we have time for questions. See the preprint for more details or catch me during the breaks or in the discussions later. Just to briefly summarize, today we looked at two components that are typically tightly connected in reinforcement learning, but we've looked at them separately. We looked at world and human action models and the degree to which they can learn complex dynamics of 3D environments purely from human gameplay data or from images and actions. And we looked at data-efficient imitation learning using predictive inverse dynamics model, which give us a way of extremely data-efficient learning of complex tasks. And with that, I'm very much looking forward to your comments and questions. Thank you so much.
Any questions from the audience?
Sure.
One question special about games is you know exactly how the world works, right? You can see perfect simulations and so on, right? Where do you see kind of limits to that potentially? Where would things break down? It's robotics tasks, you have state of simulation. I don't know. I'd be curious just about your thoughts on why this thing.
Right. It's bound to be a very speculative answer because I haven't directly worked with any physical data. As we were modeling these games, we kept looking out for, okay, here are the things that the model just cannot learn. And so we had hypotheses over time. And as we kept training on more and more data, all of these turned out not to be true. One example was that we saw the kind of rough 3D structure and navigation emerged very, very early on in training. But initially, all the kind of continuations that we generated were empty, so there were no other players in there. And of course, Bleeding Edge is a 4 versus 4 game, so you have complex kind of interactions between players. So we thought, oh, it just cannot model these highly stochastic kind of combat interactions. But then sure enough, as we kept training, all of that was picked up. And it was purely a matter of have you trained on the right data with sufficient compute before those emerge. So there are, of course, things that are strictly non-observable in the model. With the current 1 second memory, you cannot remember what happened a minute ago. So there are some clear limitations there. In a physical setting, other sensors might be very relevant, which we haven't touched on. But my current hypothesis is that as long as we can create sufficient observability and we can tokenize the kind of modalities that we want to model appropriately, there's no reason why the model wouldn't pick up any structure that we see in an environment. There's a very hand-wavy existence proof that people are generally able to infer pretty complex, for example, physical behaviors purely from watching and or interacting with the system. And so I don't see a reason why that wouldn't empirically emerge as we go here. But of course, there are very interesting questions there on what exactly, how do we need to capture those modalities? What is sufficient observability? And like our colleague was mentioning, could we get to the point where we can actually have some notion of certifying the environment simulator to the point where we would actually trust that beyond some kind of statistical guarantee? Yep.
So with the state predictor, is the horizon K fixed or is it a variable depending on the environment?
Great question. It's a hyperparameter that is task specific and it's set empirically. It can lead to more. So typically we use a multi-horizon setup. So you might sample K and predict for that particular sampled K, which gives us higher data efficiency. Intuitively, it's related to this notion of intent, or what might be a meaningful sub-goal within this environment. And we still don't have a good way of modeling or capturing that. So I think there's some interesting work to be done on how to connect that to, in cognitive science, we know that there's some part of the brain that tracks how far we are from a sub-goal, for example. So what would be the equivalent to that? Question there? Yeah?
Yeah, maybe a bit related to like the question on games and what if you don't have similar to, well, with games, but what if you don't have the behavior cloning? Like, how do you see this also working in like a, let's say, more reinforcement learning setting where you have rewards for breaking the rules, for example, of the game? Or
you mean for the, I have to clarify, for the world modeling or for the behavior side? You mean for the world modeling side?
Yes, or for like the, well, then it's not imitation learning, but just learning to play the game with this kind of setup without the imitation part.
So, yeah, maybe quick backstory to the data efficient learning part. So in year one of the project, we threw everything we knew about reinforcement learning at the problem. And it turned out to be far too data intensive to make any meaningful progress here. So that is when we went back to the basics, we tried behavioral cloning, and then found that this was actually the way to get to the goal that we had set initially. Now the goal here was very explicitly, I have a universe of tasks where I have human experts and they're able to, they're patient enough to give me on the order of tens of demonstrations, and that is what I need to work with. And the environment is sufficiently expensive to run so that I cannot do a lot of online learning in simulation. Now, with different requirements, you might get different trade-offs, right? We see that reinforcement learning is very effective in settings where, for example, the simulator is extremely cheap and parallelizable. And I think I see this as a kind of point within that landscape of data efficiency and quality. When you have a clear reward signal, the problem, you might pick something quite different from that landscape.
Interesting to see the trade-offs.
Mm-hmm. Yeah.
Just I think a follow-up from the last question. Would it be possible to use the imitation learning actions to kind of reinforce on learning the world and human action models, how these two topics you've raised to interact and to help on the downstream tasks?
In principle, right, so the question is about how do those two connect with each other? Can you learn, the environment and the actions? There are lots and lots of connections. One is kind of task dependent on what are you trying to do in the environment, right? So you could see a learned environment model as either something in which you train an agent in simulation, or you could see a world model as a component of the agent, right? And so you could do, dagger style or other types of approaches for interacting with the simulation in order to learn a better policy for something that needs to be very data efficient in a physical setup, for example. So yes, there are lots of connections within that. The specific one of learning with, you can also think of the behavioral learning as a way of collecting data for your environment simulation. A key requirement there is that for learning the environment, you need good coverage. So you basically need a policy that
Explores.
Exactly, that explores in some notion, and exactly, and in the kind of small-scale human data collection for Quake, we worked with game testers, and we explicitly gave them instructions on here are all the possible paths, all the possible things you need to try in order to get data with broad coverage. Now, you could formulate these as reward signals, and you could train agents to do that, and there is work in that space, and there's work, for example, in Atari that shows that that can be very efficient. Again, you get into some landscape of data efficiency and compute trade-offs, and depending on your application, they might impose restrictions. But now that we have a rich landscape of these components, we can combine them in a way that works well for a wide variety of applications. There in the back. You can go first, and then we can go to Andreas after. Sure.
I was just wondering, so we know from the inverse RL literature that intent is strictly non-identifiable from observation. So what inductive biases are you putting into your system so that you get a decent intent proxy?
So for the kind of demonstration here, we used a very naive state predictor, which was a given demonstration of the expert demonstrator. So the advantage here was that there is a kind of specific path through the environment that we want to follow. And so there you can purely go along and have a heuristic on how far along the path am I, and predict a state based on that. In kind of the broader literature and the set of works that we've seen related to this, people have proposed kind of video models as predictors. So theoretical guarantees aside, in a given situation where someone sees a cup of water in front of them, typically, they pick it up and they drink. So in practice, there is a lot of structure to the behavior, to the human behavior that can be observed in such models. We had kind of similarly, we had related work on diffusion models for learning diverse but structured human behavior. And again, we can see that there is very rich structure of human behavior. It's not random in that sense. And whenever we find ways of leveraging that structure, we can see improvements using these state predictors. Makes sense? I think we're almost out of time. Maybe one last quick question?
So on the part about the predictive reverse dynamics models, so the state predictor was not explicitly actually conditioned, right? I understood it.
Correct.
So I suppose the state, so you then look at kind of histories of states, or I guess the encoder captures really implicitly sort of the actions, or kind of how does it know about what the agent wants to do somehow, right?
Right, yeah. So in this case, we only use the sequence of states, which the sequence of states is highly correlated with the actions. And empirically, I think we did have that run at some point, and we see that you get a lot of causal confusion if you do include actions. Well, thank you so much. I really enjoyed that discussion, and I'm happy to discuss after.